Hi, hello everyone. My name is Miles Lee. So firstly, I would like to thank the 1Spatial for inviting me to come here to give the presentation to share my knowledge and experience in FME. Today, my topic is FME list convergence with Python programming in ETOR design pattern. So we all know that FME has abundant transformers. It is a flow-oriented programming tool for GIS data analysis, and it has more than a few hundred official transformers and more than 1,000 published customized transformers, which is very good because we can use all of these transformers to construct whatever we want regarding the data ETL, data cleaning, and analysis. But however, in the real battle, we always have some issues. For example, when we face the complex logics and scenarios, it usually takes us a lot of time to find out the suitable transformers to deal with. Or even you are very good at constructing the customized transformers by composing multiple transformers, but it also takes you a lot of time. And secondly, to deal with the relationships among multiple types of features and calculating among these types of features can also make the logic extremely complex. And it usually makes the workbench really bloat, which results in the maintenance difficulty. And it's also pretty hard to construct and maintain the hierarchy conditional statements by just simply use the tester and test filter. We all know that in the object-oriented programming, we use if-else or switch case to deal with these kinds of conditional statements. And in FME, we use, for example, tester or test filter, or some conditional values inside some transformers. And finally, when it comes to collect one group of geometries within another groups of geometries, and especially if itself has a very complex self-calculation algorithm, the logic can be very complex and the workbench size will scale very quickly. So in order to deal with these kinds of issues, I would like to introduce the core concepts of the topics today: the list convergence with Python programming and the ETOR design pattern. So what is the list convergence with Python programming? Basically, it is to transform the flow-oriented programming into the object-oriented programming in FME, which will take lots of advantages of both of these two types of programming styles. And ETOR basically is a logic block to help list convergence and geometry restoring using geometry extraction, transforming, the processing. Here I use O to represent the P because here the processing usually contains the object-oriented programming. And then finally, the geometry restoring. So with the help of the ETOR design pattern and the list convergence with the Python programming, we can always control our workbench to a certain complexity level, not make it that complex. We keep it simple because the data stream will always diverge and converge. And then for next logic, it will diverge and converge again. So here is an example. So if you look at the graph above, we have three groups of like segments: the C group, B group, and A group. And the task here is to, firstly, we will need to calculate the average value of the C group, and also calculate the average value of the A group like segments based on the formulas right here. We will need to, for example, add C1, C2, C3 divided by 3 to get the average value of the C group. And also, we will need to calculate A1 plus A2 plus A3 plus A4 divided by 4 to get the average value of A group. And then we will need to calculate the difference between the A group average value and the C group average value. And based on this difference, we will need to apply the decreasing values to each segment of the B group. It is based on this formula. So in traditional ways, of course, we can use lots of the existing transformers and in the expanding programming design pattern styles to construct our logics. But however, just like what I said before, it will make the logics pretty complex and it will make the workbench grows pretty quickly. Before going into the FME workbench, I would like to show the view scenarios corresponding to the graph I showed. So here is the dual carriage rate, the green group and the red group. And here is a bridge collecting these two ends for green group and the red group. At each segment of the line, it has different values. So here we go. I mean, like what I said, if in traditional way of expanding FME style, the logic can be very complex. However, in our ETOR design pattern and Python programming with the least convergence, it just takes a few transformers. Like right here, I make the blue groups and the green groups and the red groups of the like segments to have the relationships among each others. Here we can use, for example, touch. We can use intersect to let the B groups like segments to touch two ends to get and collect the green group like segments and the red group like segments. And then, of course, you need to tick the box, generate the list to converge the features into the list. And after that, it will go into the geometry extractor. This is what I call E. E represent extract. So firstly, we will need to extract the geometry for each segment of the B group. And then it will go into the line combiner, what I call the transforming. The line combiner is to join each segment of B group into one very long segment. And of course, again, you will need to tick the box inside the generate list to converge the features into the list to deal with. And then we'll just simply sort the list and make the long like segment of B group into the Python caller. Here I call it O, the object-oriented programming. And after calculating the algorithms and calculating different components, we will need to explode the list and recover the original geometries. So this part, I call it the R, restoring or replacing. That's why I call this design pattern is ETOR design pattern. So here we can take a look at the Python script. Just like any object-oriented programming styles, we can define different functions, the sub-functions inside our logic. For example, right here, I define the formula to calculate the values, the decreasing values for each segment of the B group. And I defined the average functions to calculate the average value of a C group and A group. And in our main logic block, firstly, we will need to, because this is the two-dimensional list, firstly, we will need to use the index to anchor and fix one of the dimension, and then retrieve the values from the second dimensions. And then we will need to parse these values into the subfunctions we just defined. And after we get the output, we will need to fetch it back to the original geometries. So here is another example. So on these carvings, you can see that there are three types of features. The detectors, which is in the square polygon. This is a sketch detector, which is used to count the number of vehicle going by. And the red line is the stop line we call. And of course, we have the blue network, the blue row segment. We have three types of features right here. So what we are going to do here is to, firstly, we will need to calculate and aggregate the counts for the detector square. And then based on that, we will need to attach these results to the stop line. And finally, the stop line will need to find the most nearby row segment and attach the values to this row segment. So this is the scenario. Again, in the traditional expanding design pattern programming style in FME, this can take the logics to grow very quickly and scale very quickly. However, in our ETOR design pattern and using the list convergence with Python programming, the things can become easier. For examples, right here, just like before, you can see we have a geometry extractor, which is the E part in our ETOR design pattern. And then we have some transformers like the buffer, the solving, and find nearest one, and aggregator. This is the T, the transforming in ETOR. And of course, in the find nearest one or aggregator, these types of transformers, you will need to tick the box of a generate list to converge the features into the list. And after that, it will go to the Python, the O part, the object-oriented part. Just like before, because here's the relationships happened among multiple types of features. So we will need to use the indexer to anchor and fix one of the dimensions and then retrieve the values from the other dimension. And then when we get this value, we can use our define functions in object-oriented programming to calculate the results. And just like before, after the calculating, we will need to explode the list and recover it back to the original geometry shape. Okay, so the advantage of this method is quite significant. Because of the nature of the convergence, this pattern can be repeatedly used to form and serialize the complex logics and scenarios. And it can also maintain a very good programming styles in FME. For example, one day, probably if you will need to hand over the job to your colleagues, or you will need to, or for example, other teams will need to temporarily take over the job. And in this case, they can also follow the streams and the logics easily. And the jobs can be handed over seamlessly. So here is the view workbench that I programmed for some of my tasks. So you can see that each block is a logic block. There are lots of logics that gather in this workbench, for example, and the logic itself is quite complex. But however, with the help of this convergence and the Python programming, it becomes quite easy. You can see the red circle I draw here is the design pattern I use in this workbench. I use them multiple times everywhere in the workbench to implement the logic. And here's another one. You can see this one is even bigger. So the logic is quite complex. Each block represents make logic. And then I can't imagine without the help of this convergence with Python programming in ETOR design pattern, how complex it can be. It can become even more complex and make me hectic. So with the help of this design pattern, you can use the red circle one. I use this design pattern and the programming style multiple times and almost everywhere in my logic blocks. And with the help of this, I just control the workbench complexity to a certain level and make it controllable, under my expectation. So that's it. My philosophy is that instead of use heaps of strange transformers on FME, we can use one method, the basic method, that can cope with shifting problems by just sticking to a very fundamental principle. We will need to simplify the issue instead of complex it. Just like the Swiss knife. Okay, so thank you very much. And if you have any question, you could contact the senior consultants in 1Spatial. And of course, if you are interested in my topic, you can also go to my LinkedIn to read some of my articles. I write it detailedly about this convergence programming style and the design pattern. And thank you very much. I will hand over to Emma.